When people talk about a large language model today, they usually mistake the isolated engine for the complete car. A base model is strictly a neural network trained to execute one mathematical function, calculating the probabilistic next token of an input sequence. Because of this strict limitation, a raw language model fails at enterprise-grade tasks out of the box. It has no real-time memory, and it lacks the ability to access external systems or current data. To make the model useful in production, software engineers spend their time building the application layer around it. This practice is known as context engineering. We can map out this modern AI engineering stack by breaking the system down into 3 distinct layers. Layer 1 is the engine itself, encompassing the internal mechanics that process and calculate language. Layer 2 is the wrapper. This is the context engineering layer, where the system connects to external APIs, rules, and memory databases. Layer 3 is deployment, where engineers optimize the physical limits of compute and memory to actually run the system economically. Mastering AI engineering requires treating the technology as a modular software architecture blueprint. We start the system blueprint here, at the foundational base model. To process natural language, the engine first performs tokenization. This breaks the raw input text down into discrete computational units called tokens. The process follows linguistic structure, separating root words from semantic suffixes, like ERs or ING, to identify specific actions. This scatter plot shows the next step, vectors. The model translates those tokens into spatial coordinates, representing their meaning in an n-dimensional space. The core rule of this vector space is that semantic proximity dictates spatial proximity. Words with similar meanings cluster tightly together, while opposite concepts are pushed apart. However, static vectors cannot resolve ambiguity. The word apple exists as a single token, but it could represent a sweet fruit or a massive technology company. To solve this, the engine uses the attention mechanism. Attention analyzes the surrounding context tokens in the sequence to pinpoint the exact meaning. If the surrounding sentence includes the word revenue, adding that vector mathematically pushes the apple coordinate toward the tech cluster. If the sentence includes the word tasty, the attention operation redirects it toward the fruit cluster. The physical algorithm executing this is the transformer. It uses stacked layers of these attention blocks and feed-forward networks to continually manipulate vectors until it can accurately predict the next word. The engine does not understand English. It calculates massive, dynamic geometric relationships to output high-probability text. Training these engines require massive datasets. Self-supervised learning allows engineers to train models at scale without relying on expensive, human-labeled data. The system learns by masking sections of existing data. If the model reads at 2 and the next word is blanked out, the network is forced to guess the missing sequence. If the model predicts Brutus, the weights inside the neural network are validated. If it guesses Caesar, the internal weights are penalized. The structure of the input data itself provides the correct answer. Once the base model is trained to predict text, it undergoes fine-tuning. This aligns the model's behavior to eliminate undesirable responses and adapt it to specific tasks. In a fine-tuning phase, the model is fed a series of strict questions and answers. If asked, "Who is the US president?" the model might probabilistically generate, "I would like to know that too." Fine-tuning penalizes that conversational tangent, updating the weights so it strictly provides the factual answer, like Donald Trump. To map user satisfaction directly onto the vector space, engineers apply reinforcement learning with human feedback, or RLHF. The process relies on behavioral conditioning, mirroring the psychological experiments of Ivan Pavlov. Like a dog expecting food at a bell, the model learns to favor certain output paths based on past rewards. Humans review 2 potential responses and assign a +1 to the better output and a -1 to the worse. This creates zones of positive and negative scores in the vector space, turning text generation into a mathematical hill-climbing optimization. The flaw in RLHF is that the model does not build a mental understanding of physical reality. If tasked with predicting a fair coin flip, a human knows the odds are exactly 50-50. The model, lacking an internal representation of physics, simply plays the odds based on which past answer generated the most reinforcement. To compensate for this logical deficit, engineers implement a workaround called chain of thought. By training the model to explicitly output step-by-step reasoning tokens, it breaks a complex query down, deducing the logic sequentially before generating the final answer. These alignment and reasoning techniques do not teach the model facts. They shape the topological landscape that guides its math. Shifting focus outward, we reach the application wrapper, where engineers inject real-time context. A simple technique is few-shot prompting. The system augments the input by appending formatting examples directly to the user's query before sending it to the model. For massive scale, engineers use Retrieval Augmented Generation, or RAG. This allows the system to inject hundreds of proprietary company policies into the context window. To fetch these instantly, the server relies on a specialized storage system called a vector database. The vector DB searches based on semantic proximity, not keyword matching. If a user's query says they are upset, the database retrieves company guidelines dealing with low ratings or drop-offs because those vectors are mapped closely together. RAG provides deep context, but it is strictly read-only. The model still cannot act on the information it retrieves. To solve that, the Model Context Protocol, or MCP, provides a standardized bridge allowing the system to interact with external tools. When a user asks about flights, the LLM flags a need for external data. The client hits the airline's external database, retrieves the live schedules, and returns that specific context to the model to formulate a decision. MCP also permits the model to trigger an outgoing execute command. Once the user confirms the choice, the model hits the airline's API again to physically book the flight. The culmination of this wrapper layer is the agent. Agents are long-running processes that combine RAG memory and prompt summarization and MCP execution to achieve user goals autonomously. Context engineering takes an isolated mathematical calculator and transforms it into an active, connected system. Running this blueprint introduces strict engineering realities. Production environments are constrained by physical compute limitations and high memory costs. To manage this, enterprise deployments frequently utilize small language models. Instead of hosting a massive 300 billion parameter foundation model, companies deploy highly specialized proprietary models with only a few million parameters. Engineers create these compact systems through a process called model distillation. During distillation, inputs are fed to a massive teacher model. The smaller student network observes the outputs and continually adjusts its limited internal weights to mimic the teacher's results. Once trained and ready for production, engineers apply quantization, a physical memory optimization executed at inference time. It compresses the numerical precision of the model's weights, truncating 32-bit floating points down to 8-bit integers, drastically reducing the RAM required to generate responses. The architecture is complete. A discrete text token is mapped in a vector space, calculated by a distilled and quantized engine, wrapped in live contextual databases, and deployed as an autonomous agent. Beneath the external presentation, artificial intelligence is a measurable, modular software architecture ready for engineers to build upon.